All right, hello everybody. Let's get back into this idea of using Gibbs free energy as our metric of determining whether or not a process is spontaneous or not. So let's look at this example here that I've provided for us, where we are trying to determine if the formation of sodium chloride solid from its constituent elements is spontaneous at room temperature. And I've given us some thermodynamic data about that reaction. So remember, the standard enthalpy of formation, or in generally like the formation of a substance from its elements at standard conditions, is the formation of 1 mole of that substance from its respective elements. So we have solid sodium and chlorine gas. And since at standard state conditions, we are forming, in fact, 1 mole of product, we could balance this so that we would have to then double the sodium and the sodium chloride. But we want 1 mole here, so we are going to be lazy about this and put a 1/2 in front of the chloride gas. Chlorine, not chloride, chlorine gas. Chloride is the ion. Okay, I have given us some information here. I know that for this reaction, the standard enthalpy of formation is negative 411.12 kilojoules per mole. And since we formed by definition 1 mole, I'm just going to drop the per mole. I'm going to leave it as implied. So this is going to be negative 411.12 kilojoules. And then I have also told us that, like, when this crystal exists, its standard entropy of this solid is this. So that's 72.11 joules per mole Kelvin. Some other things that we are probably going to need, since we are looking at a chemical reaction, and remember, by definition, we identify our reactants as being our system here. Sorry, my mind had to like buffer for a minute. Let's see if I can't find these standard entropy values for solid sodium. So let's see here, I've got a table of reference value in front of me. So sodium solid, by definition, it is a pure crystal. It's the third law of thermodynamics. We have a huge amount of order, so the standard entropy is 0 joules per mole Kelvin. And then I believe that chlorine gas, don't know why I want to insist on calling that something it is not. Let's see here, Cl2 gas, it's in its elemental state again. Is that. All right, so I have our standard enthalpy of formation. So this is already referring to the amount of energy that is absorbed or released when 1 mole of a substance is formed. However, I should probably get my delta S of this reaction, even though it's kind of mathematically inconsequential. You'll see what I mean in a moment. So the standard change in entropy, this is going to be my products. So this is my 72.11 joules per mole Kelvin, minus the sum of the reactants scaled by their coefficients. Notice I could do 0 times 1 and 0 times 1/2, but no matter what, that would give me 0. So let me just confirm that I got that right, or if I'm looking at entropy or enthalpy, let's see here. I think I might have been looking at enthalpy. That's not good. Let's see here. Okay. Good. This will give us some good practice. This is actually for sodium solid, 51.2. Joules per mole Kelvin. And just like I'm looking at these values, you would also have to be given tabulated or reference values of these standard state or standard formation thermodynamic data, right? So just like when you were in Chem 210 or Gen Chem 1, you were looking at like your standard enthalpies of formation, you would be given those on a table. Here we go. Same is true here. And the reason why it's true is because just like enthalpy, entropy is a state function, meaning I can do products minus reactants and we're good to go. So let's do a bit of a reminder on what that would look like. So if I want to figure out delta S of the formation of this, so the change in entropy of the formation of this solid, this would be the sum of the moles of product times the standard entropy of the product minus the moles of reactant times the standard entropy of the reactants. So in our case, our product, we formed 1 mole by design. So that's going to be our, let's see here, what I say, 72.11 joules per Kelvin, because I have an implied 1 mole, right? Minus, okay, for my sodium, that is 1 mole times our 51.2 joules per mole Kelvin. Plus for the chloride, this is where we have that 1/2. So this is 1/2 a mole times our 232 joules per mole Kelvin. All right, our delta S of our formation of this solid at standard conditions, let's see here, grabbing a calculator, is going to be 72.11 joules per Kelvin minus, so let's look at the sum of this guy here. So that's 51.27 or 51.2, that's a joules, sorry, plus 0.5 times 232. So that is 167.2 joules per Kelvin. Okay. So then we get delta S of the formation of this crystal as being negative 95.09. So that means that our entropy decreased. Let's check our sanity here. Does that make sense? I started off with a mole of solid and 1/2 a mole of gas, and then wound up with a mole of solid. So because I no longer have gaseous particles on my product side, I have created more order. There are fewer microstates that sodium chloride solid, the products, could exist in compared to my reactants. So overall, this process has decreased the amount of entropy in the surroundings or in itself, right? So this is then going to be expressed as joules per Kelvin. And now we can figure out our delta G. That's equal to delta H. And in this case, because we are using our standard state data, this means that our delta G is going to have to be our standard state delta G minus T delta S. So this is going to be equal to our negative, well, let's pay attention here. This is in joules per Kelvin. This is in kilojoules. So how about I really quickly add some zeros here. Negative 411,120 joules. So negative 411,120 joules minus my temperature. What temperature did I say we were doing this at? I said we were doing this at room temperature, which, remember, we always express this in terms of Kelvin so that we don't have to worry about the sign of our temperature having any kind of effect So this would be 298.15 Kelvin. Okay, let's do some color coding here. Negative 41120 joules minus, open up a parenthesis just to be mathematically safe, 298.15 Kelvin times our negative 95.09 joules per Kelvin. All right, let's see what we get here. So we have negative 41120 minus 298.15 times negative 95.09. Okay, real quick notice. This is which scenario here? We have exothermic, but we also had a decrease in entropy. So that is over here, exothermic and entropy decreases. So at high temperatures, we're non-spontaneous, and at low temperatures, we are spontaneous. So let's see if room temperature is low enough for us to be spontaneous. You can kind of approximate this as being like 300 times 100. So 300 times 100 is, oh God, 300 with 2 zeros on it, right? That's 30,000. And this is what, like 411,000. So we can kind of predict the delta G is going to be negative. And when I do this, I in fact see this is, yeah, negative 38276.8.9. I'm going to go ahead and round that 9. And this is joules. So this means that we have a delta G equal to negative 382. Let's see here. 1, 2, 3. 382.77 kilojoules. That's what delta G is equal to. So if delta G here is negative, this means that we are spontaneous. So if I were to bring elemental chlorine gas into the presence of solid sodium at room temperature, these would spontaneously react to form solid sodium chloride. And they would do so because despite the creation of like a more organized product, right, the decrease in entropy, this is such an exothermic process that we are like a dispersal net overall of thermal energy, which does in fact disperse energy according to the second law, which allows this thing to be spontaneous. So you would say spontaneous or exergonic, and you can also say this is enthalpy driven at room temp. So if you need review on how to calculate things like the standard thermodynamic property, in this case entropy, or standard enthalpy of reaction, make sure that you're going back to chapter 7 and then chapter 12. But the idea here is we have like delta X standard, right, where X is some thermodynamic property. We could either use something akin to Hess's law, where we like construct our delta terms from other reactions. However, that seems pretty tedious here when looking for entropy values. So this is where we use the sum of moles product times delta X standard formation product minus the sum of moles reactant times standard X formation reactant, because standard like enthalpy or heat of formation is per 1 mole, And again, we can do this because we are looking here at state functions, right? We don't really care how we got the change because the change is calculated from final minus initial. So in our case, we can get our delta whatever term of reaction by looking at how the product state is different from the reactant state. So we can do this experimentally if we wanted to, but we can also go look at a book or a table or some kind of like a reference sheet maybe on an exam to find these values ourselves. All right. So in our next videos, we are going to shift the conversation to talk about entropy and what is going on in a system that already exists at equilibrium. So not like a reaction that like happens, like it starts and then it reaches equilibrium, but a system that like is already in that equilibrium state. And from there, we're going to kind of walk backward and think about how does that relate to like this idea of a reaction not being reversible by thinking about how is it that a reaction energetically was able to get from its reactant's initial state to that equilibrium state. So we will be looking at some non-standard conditions of equilibrium after we look at our equilibrium conditions in our next few videos.